present day protection systems, device systems, circuits, they are not operate at such, they are not start to operate at such low level of voltages and power, and we have some other issues with keeping track of reactive powers and so on. So that is a typical configuration for a data center. I have here one which is a typical configuration for DC, and the most important is this one here. So we have in average for a data center, the overall efficiency is 77%, or in the range of 75 for an AC system, and it's 85 for a DC system. It's about 10% difference. And with the proliferation of the data center, that is a huge saving energy for the system. So that probably will move to have more and more hybrid systems. I work in both for AC, DC, hybrid microgrid control and operation. So the stability example for AC, we have here a traditional model that is for a synchronous generator. So we have here the active power. It's the generated voltage here, it's voltage to the transmission, and it's the synchronous reactance of the generator, and we have here mechanical equations. So everything we up with the equation like this one, which is the swing equation, that we adjust the torque angle based on the keeping track of active power. And that is an example how we build a stability analysis for that. So we basically keep track to the torque angle, we adjust that, and we can establish the power, the active power at the level that was big, for example, a fault or suddenly increase of load demand or change in the load demand, especially in the increase in the load demand. That is actually a simplified version of the equation. So most of the use is this equation that we have the torque angle and the speed, the actual speed, and the generator, and here is the synchronous speed. So that is how we use. So we keep track and we measure the active power and the reactive power. With active power we can adjust the frequency, and with reactive power we can adjust. And the most we use the so-called group or proportional control scheme. Use in AC microgrid. So for a DC microgrid, it's actually we know if you have a control of frequency, because it's DC, the only thing we keep the control of the voltage, and we have the power load here, so which is the current. Basically we have power over voltage here. We have an equation that is this one here, so that will keep track based on the impedance measurements for such microgrid. I have here an example with some data, and we can have example if the capacitor voltage in here, so when we have the capacitor, the voltage are low, so we can have very large oscillation, and we may end up with the collapse of voltage across the capacitor, which is basically voltage across the load. So if we include a DC-DC converter like a buck converter here, the similar is for buck boost. Buck converter is only step down, so it's reduce the level of DC voltage. So they are basically like a transformer, so you can step up, step down, or keep the voltage the same. You can improve the quality of the voltage. So we have the equation, and we try to keep the operation of the microgrid by controlling the converter in this area here. So which is the stable area, and we have lower oscillation, which are much closer output voltage like DC1. So with the traditional controller, PI controller is not working. Usually you may add a buck converter, you can change. We have here the equation, we have the parameters that are the resistance, inductances, and capacitance. We can change either one, like the resistances, so inductance, capacitance. If we change the resistance, example in this system here that I have the value, so we still for open loop we have long oscillations and voltage ripples which are not desirable. We want to have a DC signal here. If we change the resistor in the solution, it's very efficient. Even if we reduce the can use to other filters, so improve the filter. We still have some ripples. The capacitance in the filter could be expensive, and large capacitors tend to be not very robust in operation. We can add bulk energy storage. It's similar. It's for some microgrid configuration can be advantages, for some others maybe not. We get the pretty good results with that. The other one is to have adaptive and to keep track and to have a very good control of the duty ratio and the frequency for the buck converter. And that I have example here, two nodes connected to the same buck converter. And we can clear, example here, we have the voltage without not introduction of that converter. After the introduction of the converter and including that adaptive control. Here is the equations. I will go a little over that equations. We can get a pretty stable after the fault of the voltage and the clearance, similar voltage and the current. So that is actually the entire set of the equations and how we do the control for keeping the voltage in that range and reducing the ripples of the voltage. So that is an adaptation of the group control having only the voltage. So we actually check only the voltage here. It's a DC system. And that here is how we can get for difference of connected and disconnected the sources and how the system is working and keeping the level of voltage in a stable area. So that is for the, I'm moving right now to use the example, it's a new concept to use converters, and that is the virtual impedance. So you use a power converter in place of an impedance, you reduce the losses, but you still have the control of the voltage and the systems in for a microgrid. So that is the new area. So basically that is the model that we use right now, and here is the control procedure that we use. Here is the real and the proposed virtual impedance to control the power flow, to control the stability of the voltage. This is still work in progress. So I'm planning to have a paper published sometimes during the summer. So that is an application example for a system that is installed that we have at Desert Research Institute in Reno, Nevada. So we have here is a hybrid microgrid. So we have a DC bus, we have EC bus, we have a diesel generator. Here we have grid connections. We have an EC bus, we have here EC loads and batteries that we have. So that are the control schemes that we use for the system. And here we have example of the voltage, and we have the stability of the voltage that we have, and here is the profile from that photovoltaic network. Yes.
What is the anti-islanding algorithm? Prior slide.
It's the microgrid. They can operate what is named grid connection. When you have the system still connected to the grid and you trade the power with the grid. So if you have excess of power, you sell that power to the grid. If you need some extra power, that you take the power from the grid. If happens something or you decide not to operate with the power, you can move to the standalone or landing mode. The other thing, you need to control how you disconnect and connect to the grid, because you may have issues in terms of stability of the system. So that is the anti-islanding mode and the control of the system.
Right now, a lot of systems that are sold commercially for small grids is if the grid goes away, they should shut down.
Yes.
And that's for safety.
Yes. Yes.
As
that
opposed
is
to,
one.
because they don't have the ability to do the connect and disconnect safely.
Yes, that is. Plus, we have issues with most of the circuit breakers are designed for present-day grid, not for a grid that is operated at much lower voltage. you have a much lower difference. Usually you track example the ratio between the impedance and the reactance of the line to see if you have a short circuit or not. So that it's feasible for a transmission line with much larger time of response than the microgrid, which need a much shorter time of response, and you don't have such tracking system of the ratio between the impedance and the reactance of the resistance and the reactance of the transmission line. So that there are the issues that we have. So the microgrid will be critical for integrated renewable energy and distributed generation, because you move the control from transmission system operator or for distribution system operator center to a local, so they monitor, but they need to have that communication in real time, and you need to have a much better control. And from procedure to the circuit breaker systems and devices, circuit protection systems and devices. So
What was V2G?
V2G, there are electric vehicles. So if you want to include that, it's one of the trends. I am a little skeptical that will be used on a large scale. It's one of the that is proposing like energy storage system. So you can use that the vehicles to get power from the grid, but also you can use the vehicles' capabilities to store energy when that vehicles are not operated. I'm a little skeptical.
For your new Tesla. Your
So
Tesla, when you're not using it, can be hooked up to supply power to the grid in
supply
an
power
emergency
to the
situation.
grid. I am a little skeptical because it's a lot of stress, a lot of instabilities, and we'll see. So my future work is right now. I'm working in to develop reduced order model for the major components that we have in the microgrid, from wind turbine, photovoltaic, storage elements, also for power converter. I'm moving to metering. I'm working with, I didn't include here, but it's named the conservative power theory, which is an adaptation of the traditional power theory for the microgrids, especially in terms of metering and accountability in the microgrid. That are my major area of research that I have. So this is my last slide. So the smart grid and is not a 1 or 2 years project. So it's a very long-term project, probably will take 20 to 30 years. I don't like to make predictions, but that is one of the that I have. We need everyone to be involved, that from governments, academia, utilities, companies, and so on. Will be a very large change in the power system that we have been the same that was 60, 70 years ago when we moved to the local power generation to the larger grids. So, and I have time for questions and any comments that you have. So thank you for taking your time and attending the presentation. Yes.
So, you went through this very, very quickly, I understand. At some places, I thought you had referenced a variable impedance for a load, and perhaps it was time varying. And if you did have a variable impedance, which might have been time varying, wouldn't that, how do you handle the nonlinear equations that result?
We would usually discretize them.
I'm sorry?
We discretize them and we reduce the, if that is the question, it's about the equations that we use, the nonlinear systems. We discretize, and if I mention, I'm working right now to reduce order models that are a little more simpler and that can be a little easier to be handled in terms of power, stability, and control. Otherwise, it's the same like you use in computational electromagnetics. the Maxwell equations describe you any electromagnetic wave propagations, but you cannot calculate that. In most of the cases, in large number, you need to reduce, to discretize, to reduce the order, and to make simplifications. We done the same here. I don't know if that was it's your questions. I'm not sure if I got exactly the question.
No, I think I understand what you were saying. Basically, you're approximating things.
Yes.
Okay.
Yes. You cannot handle, especially if you want, example, to operate and to have a control for a microgrid in real time, it's impossible to do that. And you can do that only for a very simple model that you don't need a micro. It's like to calculate, to applying the Gauss equation to a cylinder. You don't need to have a computer to calculate that. It's a very simple system. But that it's useless in most of the other cases. So if you want to design an antenna or a transmission, the same is here. So we need to simplify to approximate. And even if you remember on one slide, I mentioned that reduced order model. So it's even for, I have here, so I'm working to have even much simpler system that can handle in terms of computational requirements and so on. For example, for wind turbine, for photovoltaic system, for a fuel cell, for a battery storage. So, at what level I can go, that I don't know right now. It's a very tough question. So it is very simple and a very if you approximate too much, you get something that is not similar, useless. So because you can get a very wrong idea what are the results and that control protection and so on.
And the utility companies have come a long way. And I worked at Commonwealth Edison as a student. The only thing they watched was the frequency of the overall system. And if their clock got behind the National Bureau standards, they pumped more energy into the system. It got above, they slowed down their fuel supply into their generators. And that was the only control they had. And at that point, they wouldn't let the computers control the system. They would let the computers do calculations, and they looked to see what the computer said to do, and then maybe they would follow it or not because they didn't trust it. Today, the protection schemes are far more sophisticated, but we still had a blackout in 1977 here at this coast.
Some of them they are due to the operators, some of them the human factor is a big issue in power system. The largest blackout in 2003 was the human error, basically. Was an increase in demand of energy due to the very hot days that were in that time, and the operator that was in charge was from a transmission operator center in Ohio area, so decided to go first to the launch and took back and fix the problem and increase the efficiency. When he came back from the launch, was too late.
Basic question. It seems like if you have all of these people with solar and wind, and then the wind dies down and the solar dies down, how do they make the big generators ramp up so quickly to generate steam and fill the void? Because when you turn on the light, you don't have to wait.
This is not a big issue.
Oh.
Because the system, that was the idea that you interconnect the system and get what is named the infinite bus. So it's a very stable, it's a very large inertia, so a large number of loads that can connect and disconnect, a large number of generators, they may have malfunctions, so they disconnect the power system. Power plants usually they have at least 1/3 of the capacity in backup. So they are not operating, it's probably some of them even, I don't know, here in the United States, but in Europe you have about 60% in Salem that you have from a power plant that operates at full load. The other 40% is in maintenance or backup.
Because it used to take time to ramp up.
You connect that and you have the power. The system is so large